Hello, absent people. We miss you. So we just went through, there's some questions for question 6. And let's be honest, some people hadn't done question 6. So we went through this one. Hopefully you can follow along, and ideally you don't look at this until you've actually done it yourself. I have left my errors for all to see. So forgot to times everything through by 3 there. Special K found that one, so that was great. And what we did was we just tidied this up, and when we noticed there was a common factor, so we could pull out the common factor, factorised it, factorise this as well. So that's how we ended up with the last bit. It is a bit ugly, so when you got down to, hopefully everything to this bit was okay, but when we got to here and we had to try and get a 0 there, it was nasty. So we had to times this whole row by 3, but this all one by m plus 4. Not pleasant, but huzzah. And now we're about to carry on. Hopefully you're reading there. The part A, I don't want to scroll back up so you can look at it actually better, just in case. Hopefully you've got the question in front of you. But, oh, I didn't even cut and paste it. Well, there you go. Can't do that. Here we go. Did I have it here? Show that the system has no solutions for one value of m. And we'll get to the interpret in a minute. Let's just do one thing at a time. So what does that mean when it's going to have no solution? You know, go back. Remember that was if it was 0z equals something. Yeah, as long as a was not 0, right? When we have that, it's ridiculous because it's saying 0 times something equals 5 and blah, can't do. So, very clearly, what value would that be? Correct. So, no, can't be minus 1. So they said minus 5. Minus 5, yes, would give no solution. So when m equals minus 5, what happens to the bottom row is it becomes 0, 0, 0. But then the right-hand side, minus 5 plus 1, it's minus 4 times minus 28. And there we go. That's impossible. That's no solution. If m was minus 1, it would be 0, 0, 0, 0. And for that at the moment, that could be infinitely many solutions. To see if it was anything more, we would have to then also put it back into the next row and sort that out. So at this point, m equals minus 5 are no good, no solution. And then let's have a look at the next one. Interpret this result geometrically. So what does that mean? Trains, planes, automobiles. We have to go back and pop the 5 in here, and we're checking for what? Right, if they're multiple, if it's parallel. So a multiple means what? If it's one multiple of the other, means the planes are coincident, one on top of the other, bless you. And I think we can see straight away, no matter where we put the minus 5, it's not going to be one plane is not a multiple of the other, one equation, and it also isn't going to be like the same A, B, C and a different D. They're all different, okay? So that would be, that we've got totally different planes, and therefore that one, yeah? You can't see at home. Whoop, this one. Happy with that? We already discussed the next one, but hey Tom, thanks. Show that there are infinitely many solutions for another value of m. Correct. And we discussed that one before. So when we've got minus 1, 0, 0, 0, 0, boom. Obviously put it into that one, and that's when you're going to let the z be t. And so when you do that, let z be t, what does that mean? It means they might, so you've got infinitely many solutions, but it means they might be meeting along a line. To know what is exactly going on, once again, you would have to replace now this with minus 1. And what do we get? So can you notice this would be, that's minus 1, minus 2, minus, oh, just still 1, 1, 2, minus 1. So these are reversed. And this is reversed. So these two planes would actually be coincident. If it was 1, 2, minus 1 and 7, then they would be parallel. Does that make sense? So these two coincident, it's going to meet this one at a line. And you would find that by letting Z or Y be T and carrying on. So we understanding how we can interpret all these. And what's the last one? For what values of M does the system have a unique solution? Interpret this result. So that would be, if we just look at this, looks a bit ugly. -2. I don't know where my -2 has come from. They didn't have the -2 is what you said. Anyway. Well, you might have to suss. I've done something somewhere. Did you end up with a bit of debate going on because we looked at the answers just then, they didn't have the 2. So go back, look at the work solutions, you can suss it, but it's all much of a muchness. I'm not overly concerned at this point in time. But what happens is you end up with this, Z equals 7. And then to get Z by itself, it's divide by, so they basically cancel out. You can get an expression for Z equals that over that and so on. Bit of a pain in the butt to then go and get a Y and X. I think that's just a bit of time wasting, to be honest with you. Yep. So that one's really good, just making sure that you interpret those bits and pieces. So homework is now going to be to finish those up to and including 7. You have to do 8. And then we're pretty much done with all of our vector paraphernalia. Remember, we didn't do question 1, 2, and 3, but that's basically, you would have the third row 0, 0, 0, because you've only got the first 2. So it's going to be 2 planes, and they either intersect at a line or they're parallel or coincident. There's not going to be a unique solution for 2 planes meeting. Do you all understand why? Just can't do it. Impossible. So we are now backtracking into chapter 5 and exercise 5H. As always, you can go and look at the examples, play around with them, but we are starting with this one. Have a look, have a think for a minute or 2, and then we'll go through. So I've asked people to go and look at the revision sheet, summary sheet that I gave you. So I wouldn't expect you to do this without a little bit of a nudge from your loving teacher. So we've got the summary thing. So can we all see that? It's on the right-hand side of the first page, those properties. Can we see, can we see, can we see? At the top, number 12. Everybody with me? Okay. So we want to show algebraically, that's why we're going to be using some of these properties, we want to show this. Now our actual A for us is actually A plus B. So I'll start with the left-hand side. A plus B squared. So using this property, what would that then become? Everyone happy? It would be A plus B dotted with A plus B. We good with that? And then we're going back to our properties. How do we expand that? Right, it'll be A dot B plus B dot A plus B dotted with B. I got a bit excited too that I didn't specifically read it. I'm hoping you read the question. So A and B are 2 position vectors, distinct points A, B, neither of which are at the origin. Show that then A is perpendicular to B. Now there was nothing stopping us doing the geometric first if we really wanted to, but we're going with the algebra. As soon as we've got this happening and we see the dot product going on, what do you think we're trying to aim to do? Make what equal 0? Yeah, so when we've got A is perpendicular to B, we're hoping to somehow end up with this. Would you agree? That's the only way algebraically I think that we can do it. I mean, what's the other option? To find the angle, so cos theta, blah, 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 but we've got no other measurements. So it's really, this is our last course. Okay? Anything else that we can do? What else do we know? Look at your properties. Can we simplify that at all? Yep. So A dot B is the same as B dot A. So we've got, an A dot A, we could replace back to that if you wanted to, but because I've done, we might as well, okay, can do. Doesn't make a difference, but it's one I've done before. And now I've hit the wall, right? Hit the wall a little bit and gone, So what's then another plausible thing that we could do that we haven't tackled at the moment? This is our left-hand side. And just as I said, because I've done this before, just going to put it here, level. And they sort of said that they equaled each other. Now, most of the time when we do a proof, it's do the left-hand side, try and make it equal the right-hand side. In this case, did the left-hand side if. Anyway, away we go. Following the same situation, you do. And I'm being a little bit sneaky here, all right? I guess I should have told you from the beginning, leave a bit of space. You've probably done it underneath because your page isn't that wide. But technically, the left-hand side equals the right-hand side, yeah? So we keep on going. Do we agree? If I hadn't done the left-hand side, just did that by itself, at this point in time, can you see anything that we could deal with? Because the left-hand side actually equals the right-hand side, agreed? So what can I do? Yep. Because I had written that, I might as well just simplify then this as well and go A squared. You agree that's the same as minus 2A dotted with B? And if I'm sucking up, I would have actually written the properties that I have used. So I've got that one up there. I would have probably written somewhere here that A dotted with B equals B dotted with A. Yeah? Okay, so these actually equal each other. So now you've got one of these on one side and one on the other side. They cancel. You've got one of these on one side, that on the other side. What would be my next step? What are we trying to prove?
Bring to minus 2 to the other side and equal to 0.
So what I have here, and it looks a little bit messy because of the way I did it, but on the left-hand side we've got 2A dotted with B equals minus 2A dotted with B. And you go, well, yep, get everything over to one side. So we end up with 4A dotted with B equals 0. And the only way that that can happen is if A dotted with B equals 0. Therefore, A is perpendicular to B. So now we're going geometrically. So two vectors, and A plus B is the same as A take B. So when you said complex numbers, I guess it is a little bit like that, I guess. If we've got two vectors, shall we let one be A? What do you want the other one to be? I sort of want to go up, but I don't care. You want to go up? And I'm going to make them different size. So that's B. So if we have A and then we've got B, this one here, oops, oh, bored, keep up with me. Oh, it's curvy too. That's A plus B, do we agree? And minus B, I could put it down here, but we're using some of those little tricks we did. Oh, good. Those little tricks we did with complex numbers. So that is your minus B, correct? So A take B would be that one there. And the only way that they will actually be the same, I should have made it a little bit different. The only way they can be the same is if, no, not a rhombus. Wouldn't it have to be a square? Because a rhombus, the diagonals would be, oh no, they could still be perpendicular. No, but the diagonals wouldn't be the same length. So what we're saying is these have to be the same length. So if we had a rhombus, that diagonal is shorter than that one. The only way that it would actually be perpendicular is if it was a square, and then they're the same. No, a rectangle, once again, your diagonals, oh, but they're not at 90 degrees.
But A and B are perpendicular, not A.
Oh! A plus B. I keep thinking A plus B and A take B. Sorry, same length. Yes, agreed. That's your A, that's your B. Agreed. Correct. So you can prove that all of the sides, so two pairs of sides are parallel. That would do it. But most of the time, the easiest way to prove that something's a parallelogram, if you could prove two lengths are parallel and the same. So especially when we're doing vectors, like if we can prove that MN is the same as QP or MQ is the same as NP, we're good to go. Okay? The problem is there's nothing on there. What are we going to do? So a simple thing that we can do, and so we're all on the same page, is we are going to call midpoints of the sides as shown. We're going to label these big vectors, okay? So do we want to call this one, call that one A, call this one B, call this one, you're on the same wavelength, and call this one F. You should be afraid, be very afraid. Yes, but anyway, so MN. If we are being really good, M to N, I would say is MB plus BN. And now I'm a bit tired of being very good because really I should say that's half AB, but I'm just going to go, yeah, man, that's just a half, oops, a half A plus a half B. Okay, so far so good. And we're a little bit lost, and that's minus a half D plus C, C plus D, right? So now we're in a bit of poo-poo. Because what we were trying to aim for was that this was the same as this. This is A's and B's. This is C and D. And you go, I mean, I could go a half A plus B. We need a link. We need a link between these guys. So the only clue I'm going to give you before Sam, he's dying to come and do it on the board, but I want you to look at your diagram and I want you to try and have a think about what is this? And maybe look at what's C plus D. We're nearly there. So I want you to think about, now I'm going to show you on the board, and you should have done this with your finger, A plus B. What is that? I don't want to introduce another colour, but I'm going to. Right, A plus B is in fact AC. What is C plus D minus or whatever. So are they not? The same? Same. How clever was that? So how do we do that? I mean, we could just, it's up to you. You could work out and say that AC equals, so A to C equals minus D minus C, which is minus C plus D. Sub that in. So therefore, this now equals a half AC, which equals MN. Therefore, MNPQ is a parallelogram. I would also, if you're doing something like this, right at the start, right, explain what is it now, what's your plan about proving that something is a parallelogram. It doesn't have to be write it in maths. You could just say, proves that. All right, that could just be to prove that MN equals QP. One pair of sides, parallel and same length. Put that reasoning down. Okay, so first thing, we've got our rhombus, like so. Hi! Okay, so with a rhombus, we know that they're the same length. We also know that this is parallel to this and that one is parallel. Now, you don't have to write all of that in if you don't want to. This is just something that we know. And so we could call this one A and this one B, and then the other vectors are obviously, like if we added a length here, then that would be minus A, and that one would be minus B. Is that okay? By the way, I'm going straight to the vector methods for this because it's just... So what are we trying to do? Prove that the diagonals of a rhombus bisect the angles of a rhombus. Oof. Bisect the angles of a rhombus. Work, row-ups. Feel free to start any other revision, and if you want to have a think and play with that, you can. And you need to do A and B of question 4. A and B of question 4.